All right, we're almost cooking. Are we cooking? We're cooking. We're cooking and we're cooking. One, two, three. Good. And streaming is a go. Okay. Hey everybody. Today we're gonna do parabolas. Parabolas and quadratics. How should I put it? I've decided to break the lesson into three parts. So in the first one, we're not going to do any algebra. No algebra at all. Okay? And in the second one, it's going to be all algebra. Which will be kind of mirror the one we did with the linear graphs when we were talking about just the various forms of algebraic expressions that are linear. We're going to do something similar with quadratics. And that's going to be kind of a haul, but you know, you've spent enough time mastering. That's the point of all this. You've spent a lot of time mastering the quadratics, completing the square and stuff. Anyway, so that's going to show up in the next lesson, 4B, and then after that, I'm going to teach you how to graph. Okay. So right now, all you need to focus on is just the graph. So we're going to be talking. So at the end of this, you'll be able to recognize the different attributes of a parabola: vertex, axis of symmetry, x-intercepts and y-intercepts, and given half a parabola, you want to graph the other half. Okay, it's a pretty fun little skill. So let's start. So I mentioned that like there were Greek people back in the day, and they were obsessed with geometry. And Greek geometry was obsessed with a bunch of shapes. Like you know all about circles. Maybe you did circles in high school. And triangles, we talked about similar triangles, you know, that. You might have learned some proofs using similar triangles and some right triangles, and there's Pythagoras and all that, right? Well, Greek geometry went past that. There are some other shapes that you might not have heard about. These shapes are often called conics. And there were special shapes. You might have heard of some. A circle is one type of conic shape. Circle. There's another one called an ellipse, which is an oval shape. There's another one called parabola, which we're talking about today. And there was another one called a hyperbola. Maybe you've heard people say, oh, you're being hyperbolic. Well, that's in reference to a shape called the hyperbola. Hyperbolas look like this. Okay? And it turns out that all of these different shapes have various aspects to them. We can talk about them in a variety of different ways. I don't think we have enough time to do too much conic stuff in this particular course, but they're super fun. There's all sorts of attributes about them, like one of them is the defining property. Greek word for that is lemma. No, it's not lemmas, it's locus. Sorry, it's been a while since I did this Greek. Locus, which is essentially what all the different points on our curve have in common. So a circle are all the different points that are the same distance from the middle. And so you can draw one with a compass. An ellipse has two places called focuses. So an ellipse, you have 2 points. It's called the focuses. And then you take a string. And the string is the same length, and you tie one string to this end, one string to this end, and then you take a pen and you put it in the crook of that string, and you can move it around. So over here and over here. The string always has the same length, and your pencil will draw out a shape like that. Okay? The ellipse has, or the hyperbola, oh, I forget what the locus of the hyperbola is. The locus of a parabola is actually really neat. What it is it's a curve, okay, where the distance between this line and essentially what we call the x-axis is the same as the distance between this line and a special point here called the focus. Okay? So what you do is you say, okay, well, all these points have the same distance from the focus. And that's kind of neat. So this particular thing gets used a lot in lens design, like in astronomy, or maybe you've heard of a camera where you have a certain type of lens, a mirror lens. If your mirror lens is shaped like a parabola, then light that comes in like that will all bounce back and hit the focus. And that's essentially how mirror lenses work. They're shaped like parabolas. Anyway, the long story short of this is, you know, the Greeks were like, hey, look at all these cool shapes. They all have these unique properties where we can say all these points on this line have something in common. And one of them was called the parabola, and we're going to be talking about the parabola today. Ooh, violet. Parabola today. Okay? So you don't need to know about all this locus jazz. I'm just giving it for context. The deal is that we knew all about parabolas since forever. It's one of the basic types of shape, like a circle's a basic type of shape. It's not something you talk to little kids about, because essentially you're like, hey, little kids, there's the special shape, and they're like, whatever. But you know, if you're into geometry, it's certainly one of the really helpful shapes to talk about. Parabola. Okay, so that's just context. You don't need to know about it, and you could probably look up YouTube videos about it if you want to know more, because I'm not going to test you on any of that. So let's talk about basics parabolas. Basics. Parabolas look like this. They're shaped like a U. Sometimes they're upward shaping, sometimes they're downward shaping. They're never sideways shaping. So they're either shaped like a U or an upside down U. I mean, there's something more specific to them than they're just, you know, bowl shaped. There's more to it. You know, there's that locus argument. But essentially, in terms of the general shape, they're not flat. They're curvy, and they're curvy like a U. Okay? So let's talk about parabola basics. I went on to, there's a software program you'll learn to use if you take Math 101, and it's a math software that lets you plot things on the computer. So I have plotted some shapes. I've plotted a bunch of parabolas just so you can see what they look like. Parabolas are kind of U-shaped, like I said. They bowl down at the bottom. That's very interesting. Okay, so first thing to know about parabolas is that they are, if we think about them as functions, you remember functions, look up some value of x equals 6, and then you can look up, whatever, y, the output is equal to, I don't know, 38. Just kidding, I know exactly what it is, it's 36, but I'm pretending to read this off a graph, so whatever. You know, you can just look up the value, use it to look up a value. Parabolas as functions, they have domain everywhere. Everywhere. Any input x has an output. Cool. And so, ooh, that's not it. Every parabola has a y-intercept. Okay? So this one's y-intercept is over here. Looks like it's 0. Yeah, graphs are hard to read. How about this one? This one's y-intercept is, let's see, the scale on this graph is, so maybe this graph has y-intercept 4. This parabola has y-intercept, I don't know, that's not 0. Y is equal to 2. This one has y-intercept 20. All right. Long story short, every parabola has a y-intercept, if we think about it as function. What about x-intercepts? Do they all have x-intercepts? Well, the short answer is no, they don't all have x-intercepts. The longer one says, well, sometimes they intersect the x-axis in one place, and so this has x-intercept. at x is equal to 0. This one here has two x-intercepts. Because it's shaped like a U, sometimes if the U is facing upwards and the bottom is low enough, it will have two x-intercepts. So the x-intercepts here on this graph are x is equal, looks like -1 and 4 are the x-intercepts. Now, unlike linear graphs always have an x-intercept and always have a y-intercept. Parabolas don't necessarily have an x-intercept. You see, that one never crosses the x-axis. Why doesn't it cross the x-axis? Well, it's downward pointing, and also it starts out, its highest point is below the axis, so it turns around before it can cross the axis. So it has no x-intercept, which is interesting. This one has two x-intercepts. There's a variety of behavior. Okay, long story short, parabolas can have one x-intercept, they can have two x-intercepts, or they can have no x-intercepts. How about if I come up here and write that lesson out? Here's my x-axis, y-axis. Whether or not it has an x-intercept or a y-intercept, okay, so hold on. So, here's a bunch of upward pointing parabolas. This one has no x-intercepts. This one has one x-intercept there, and this one has two x-intercepts. This one is a downward pointing one. It's too low. It never crosses the axis. It has no x-intercepts. This one has one x-intercept right there, and this one has two x-intercepts here and here. Because of its general shape, it's possible to have 0, 1, or 2 x-intercepts. And this is totally unlike, this is behavior that's totally unlike linear functions. Linear functions always have x-intercepts and y-intercepts. In this case, a parabola is always going to have a y-intercept. It's going to cross the y-axis somewhere, but it may or may not have x-intercepts. And that's just because of its shape. I hope that makes sense to you. Okay. This isn't the only property of parabolas, though. There's another big, super important property, and it's a property called the axis of symmetry. Symmetry. Sorry I'm scrolling up and down so much. I thought these graphs would be a little bit smaller when I imported them. They're huge. Okay. So, something is symmetric when part of it looks the same as another part, okay? Sometimes we talk about rotational symmetry, sometimes we talk about reflection symmetry. This is a type of symmetry called a reflection symmetry, which says that if I draw a vertical line through a special point, this point here, if I draw a vertical line through it, then the shape on the left-hand side is the mirror image of the shape on the right-hand side. It's a reflection symmetry. Okay. This line that I've drawn here is called the axis of symmetry. What do I mean when I say that it's the same shape? Well, one way you can talk about this is you can, here, maybe I should get a different color pen. You can talk about it, you can draw any horizontal line you draw. There you go, there's a horizontal line. It's going to cross our parabola the same distance away. Let's see. Right? So this distance from here to the parabola is the same as this distance from here to the parabola. In both cases, it's, I don't know, what is that? 6.1? Maybe I'll show you this on another example. The deal here is, though, that every parabola has an axis of symmetry. Okay? The axis of symmetry is a vertical line that goes through the lowest or highest point. The bottom, right, that point, it's called the vertex. Okay? So long story short, every parabola's got a vertex and an axis of symmetry. So here's one that's a little bit cuddlier. Okay, so where's the vertex? The vertex is right here, the bottom. So if I draw a vertical line through it, the argument is that this shape and this shape are the same. That if I folded it over, it would look the same. They're mirror images of one another. In other words, anytime I draw a horizontal line, okay, well, what am I doing with this horizontal line thing? I mean, imagine yourself in the mirror. Hold on. Let's draw some space. If I'm on this side of the mirror, my mirror image would look exactly the same, except not quite the same. Everything about this would be inverted, right to left. Right? And so one way to describe essentially the relationship with the original and the reflection is to say, well, you know, at any particular height, at any particular location on the mirror, this place is the same as this place, and this place is the same distance away as this, and this armpit is the same distance as this armpit, and this foot is the same distance as this foot, and this leg thing is the same distance as that leg thing, and this start of the smile is the same distance as this start of the smile. And that's what we mean by like mirror reflection. And the idea is that parabolas have the same mirror image property, right? So anytime I draw a horizontal line, boop, it's not horizontal. Well, I guess it's sort of horizontal. Let's take the x-axis. The x-axis is a pretty great horizontal line. Maybe a bigger pen. All right. So there we have a horizontal line. Where it hits on this side and it hits the line on this side, every horizontal line is going to, because it's U-shaped, every horizontal line is going to hit it in two places except for there, or it's going to hit no place. So the idea here is if I draw a line up through the vertex, this distance here is going to be the same as that distance there. What distance is it? Can I figure it out? Well, this looks like it's at -1, so this is 1 space, 2 space, 2.5 spaces, and this is 1 space, 2 space, 2.5 spaces. Right? So they're mirror images of one another. I'm counting it off on the x-axis. All right, we're going to do an exercise about that in a little bit, so hopefully it's not too weird. Moral of the story, though, every parabola has a vertex and an axis of symmetry. Okay? Where this side is the same shape as that side. The vertex is either the highest point or the lowest point on the graph. So if the graph is pointed downwards, if it's an upside down U shape, then the vertex is going to be the highest point. If it's a right side up graph, like this one, then the vertex is going to be the lowest point. There you go. Okay, so where on this, take your finger, put it up to the computer screen, get your greasy fingerprint on the computer screen. Where on this is the vertex? Try to point to the vertex. That's right, it's right here. Okay? All right. So let's do an activity with this. One really fun activity is, if you're given half of a parabola, as we are right here, sorry, can you see it? This is half the parabola. We go down to the vertex, whoops. Vertex is at the bottom here. I want to sketch the other half. How do I go about doing that? Well, first I want to recognize where the axis of symmetry is. It's this line here. Okay. And I didn't even draw a nice vertical line. Come on, be nice. All right. So, I want to draw the rest of the parabola. How do I do that? Essentially, I'm just going to mirror this shape on the other side. Now, if you were lazy, you would just go like that. And that's not the right answer because it's more precise than that. This isn't just any U shape. This has a specific property. Okay, so what we're going to do here is we're going to look at these like intersection points. Yeah. And we're going to mirror them onto the other side, and then we're going to use those dots to trace. What should I mean? I mean, okay, so this is where the parabola is touching, so that's where it's going to start. And then this point here is 2 steps away, and so over here, it's also going to be 2 steps away, right? So the line's going to go through there. This point here is 1, 2, 3, 4 steps away, so at the same height, 1, 2, 3, 4, it's going to go through that point. This one here is 1, 2, 3, 4, 5, 6 steps away, so it's going to go 1, 2, 3, 4, 5, 6 over here. So we know that the line goes through this point, this point, this point, and this point, and so we can kind of sketch a mirror image, and then it goes off the page. Right? So that's an activity I might ask you to do. It's pretty fun. Well, this one here is... Oh, I want more space. Give me more space, computer. Oh, jeez. All right. Well, I feel like plotting pictures and then trying to draw them is kind of a bust, to be honest. As an exercise, I'm not having the most fun right now. All right. So let's try it with this one. We see the vertex. Try drawing the rest of the parabola. Sketch. That's the... All right. So this one is 2 away, so it goes through this point. And this point is like 1, 2, 3, 4 away, so it goes through like that point. And so the line's going to go like that. If you want to, you can erase the erased part. Oh look, it's pretty good overlap. All right. So, I have one last point to tell you about, which is, this is all very fun. Hooray! So as an activity, I want you to be able to do that, draw the reflection thing. I don't really care too much about it. Just the basic idea. It's got a vertex, it's got an axis of symmetry. There's one last point that's worth talking about, which is, jeez. Can't make it go higher. Go higher. Well, whatever. Okay. How do you find the vertex? So right now, you guys are all like, hey, it's easy to find the vertex. You just put a little thing where the thing is at its bottom. It's easy to locate the vertex visually, but you might want to know the number. So is this vertex here, is it at 2.5 or 1.5, 1.3? What do you think that value is? There's actually an easy trick for finding the vertex that comes about from the axis of symmetry, right? So remember how the axis of symmetry works. The principle here is that anytime I draw a horizontal line, like that one, these 2 points are mirror images of each other. Mirror images. They're mirror images of each other. And that means that the axis of symmetry is halfway between them. So I think I've kind of, maybe I need a lighter colored pen here. So if I could figure out how far it is between these 2 points, I could figure out how far it is to the axis of symmetry. So let me do it on this one here. So what's the distance between here and here? That's -1, and that's 4. So the total distance is 4 minus -1 is equal to 5. To find the distance between 2 points, you go x final, the bigger, minus x initial, the smaller one. All right, so it's 5. You can see that it's 5. So what's half the distance between them? Half that distance is 5 over 2, so that's 2.5. So the axis of symmetry here must be 2.5 to the right of that one, and 2.5 to the left of that one, which is at location x is equal to 1.5, which means that, and since we know the axis of symmetry goes through the vertex, we know that the vertex is at x is equal to 1.5. Okay. It's a pretty fun little activity. Let's see if any others are copacetic in this particular set of graphs I did. These ones don't have the points on it. Yeah. So let's move to this one here. I'll hold the graph up here. You try to find the vertex. Figure out where the vertex is. Try it now. Is it at -3? So what you do is you go, okay, there and there. What's the distance between them? 4. Right? And so what's the distance between this point and the axis of symmetry? It's 4 over 2. So you go 2 steps to the right of this, exactly, and so that left-hand point is at -4, so the axis of symmetry is at x equals -2, and that's where the vertex is. Okay? So that's the x value of the vertex. Pretty fun. All right, there's no room here. I'm very unhappy with this particular setup. Okay, I guess I'll do a review here. Parabolas have a few basic properties. They all have y-intercepts. Sometimes they have x-intercepts. They could have 0, 1, or 2 x-intercepts, depending on how they're going. Okay. They always have an axis of symmetry. And there's a place called the vertex. So if you're cool with those and you can do the axis of symmetry exercise, we're good. Let's move on to Algebra Town. See ya.